University in Australia in 2002. He's currently senior lecturer in the Department of Computing and Information Systems. He's an expert in the area of peer-to-peer computing, distributed systems, large-scale high-performance networks. He also works in social networks and smart mobile systems. So it's my pleasure to have Aaron, and now he's going to talk about high-performance input-output computer organization and memory.
Thanks, Idris. Just a little bit more perhaps about me. I'm not a coding theory person. So those questions really will go to Udaya. I know as much about coding theory as that there's an N and that there's a K and that we only need so many blocks to recover, right? So my area, as Idris was saying, is very much about systems. I build things, I write programs. I do coding, but it's not coding theory, it's writing software, experimental systems. Now I've been doing some big data analysis with Department of Defense, for example, stream processing of data, and all of these kinds of things. So Udaya and I have been working together because we've been really looking at the practical aspects of deploying, distributed codes in real systems. So not just the mathematical aspects, which you're going to learn a lot of in this course, I guess, but also the practical parts of it, making it all work, and the things that perhaps you don't think about when you're looking at the theory that can be important to consider. You talk about disk drives, and really, are we even using disk drives a lot of the times today anyway? So the agenda of this little talk is about some technology trends. So the first part of it is just a little bit of a kind of glossy look at some numbers and some data pertaining to some technology pertaining to disk drive storage devices. And then there's some aspects of I/O performance that are really low-level details of drives. Some of the very basic things that contribute to the storage. How long does it take, and why the throughput is what it is, and the reliability, these kinds of things that are very much under the hood. They're the nuts and bolts of and so on of the technology that eventually your systems and all your coding and so on build upon. So there's a memory hierarchy in the computer organization. It starts at the top with the registers, which are the fastest access, the nanosecond access to data that are in registers. And then it goes down to the cache, which is still on the processor. And today there's many levels of cache that your processors can have. And this cache might be shared between multiple processors as well. So you have a multi-processor system all sharing some kind of cache. At some numbers of levels of cache, there might be multi-core, I should say, as well, that are sharing some cache, and then multi-processors that are sharing another level of cache underneath that as well. And then there's main memory, the physical RAM of the machine that is essentially the main components of the processor of making the computer. Where all programs and so on are running, loaded and running. And then what you guys are talking a lot about, I think, is the storage down here under the RAM. And then beyond that, even you have here you have removable drives and network storage and hard drives and so on. But then you also have other sorts of things, removable media, backup. So if you think of memory as a storage system, it's actually many levels of storage. From very much what's readily available right now to the processor to what takes a little bit more longer time, microseconds and then what takes maybe milliseconds of time to access, and then what's taking maybe seconds or minutes of time to get to, and the time it takes to access these things get bigger as you go down through this hierarchy. But then as well, the amount of storage increases. It's why we see it as a pyramid. It's the size of the things down here. So this typically, your RAM might be, today it might be like 64 gigabytes on a single machine. That's still a reasonably big machine. I have 32 gigabytes on my home machine, for example. So that might be a typical amount of RAM, but then here you're talking hundreds of gigabytes. If it's solid state drives, or if you were buying a hard disk drive, you'd be in the terabytes quite easily. You might have a 2 terabyte hard drive on a single machine kind of thing. That's only maybe $100 or something for that. So it really does depend on the technology, on the kind of drive that it is, the kind of storage. And down here, it's like petabytes and exabytes, huge rooms full of drives that are all being somehow managed, maybe robotically or something like that. The size and the scale really increases. And this is really just, in some sense, just a single machine. It's a kind of a hierarchy until you get maybe down here. It's kind of a hierarchy of a single machine, and then we talk about distributed. So you have then, a large number of machines. Each of them maybe has 64 gigabytes. You have distributed memory in the RAM, and you have all these drives that are distributed as well. So you end up with a very large amount of storage, and then you need to understand what affects, how fast does that storage work? What is it that makes it work? So that's kind of a little bit of the context. And what I wanted to sort of say is that you guys talk about storing stuff on disks. You're probably not. In a lot of cases, maybe you're not storing stuff on disks. You're storing stuff on solid-state drives. They're very different. The hard disk drive is the mainstay still. It's very cheap. We'll see some numbers later per terabyte. And so further down the hierarchy, that's what perhaps you're using. But today, a little bit further up the hierarchy, you'll be using solid-state drives and NVMe, which is really just a kind of solid-state drive as well, but typically using a different part of the computer system. It's a bit faster as well to operate. Now these things have very different characteristics in terms of their speeds, their rates, and their failure rate, how they fail, and so on. It's things like that that could be important to you when you consider, a code that's, you look at, well, what kind of failures does it tolerate? What are you expecting from the drives underneath? Does the whole drive just fail, or part of the drive, a sector becomes unavailable, something like this? So, how do you recover? What kind of codes do you need? There are different kinds of ways that you can think about that, but you need to know what the technology is that you're making the code for, in order to make the optimal code for the purpose. So the hard drives have, these things have mechanical parts, right? There's something that's spinning in there. If you hold it in your hand when it's running, you'll feel it, right? It's moving. There's something happening. But the solid state drives, there's nothing there really. It's it has no movable parts in it. It's really only mechanical on the interface. You've just still got to plug something into it, right? That's the mechanical part. But other than that, it's all electrical. And today these hard disk drives and even the solid state drives here will typically still use a SATA type connector. Whoops. These guys over here, the NVMEs, are moving all towards PCI Express as their way of connecting, which is quite a bit faster. So the speeds of the drives and so on have changed a lot over the last 10 years even, and I think it's good to keep abreast of these changes and understand what it means from your coding point of view. Again, I just collected some things off the internet, some measurements from various places to sort of highlight some of the things that I'm saying. So the hard disk drives are very low price compared to these solid state drives, but they're much bigger capacity, as it's got price per dollar. Capacity per dollar, sorry. They have a bit longer life cycle, as said, although the solid state drives can be much more reliable in some ways. They have a lot more high power consumption. So sometimes we talk about green computing and reducing, doing the same job with a lower power consumption is quite important area of research. And a lot of times we talk about these distributed systems. We're trying to switch off as much as possible. If the drive is not being used right now, switch it off. And then just before it becomes being used, we turn it back on, right? So we're trying to save power and so on in that way. The power consumption becomes important because the mechanical parts can break down much easier, obviously, than the solid state parts. So the hard disk drives have problems there. The hard disk drives have got a lot more noise. If they use a lot of power as well, you end up with more fans actually running in the system, so you have more components that are required then in the system as well. That generates more noise as well. So really moving to the solid state drive is the way everything is happening. I would not buy a computer today with a hard disk drive. Okay, I would only ever buy solid state drive computers for my own personal use, at least. If I wanted a huge amount of storage, maybe I'd get hard disk drives. So the access times so here's a chart, and again, I know you can't really read this, but I'm kind of just going to read off some of the numbers just to highlight even more. So the access times of a typical hard disk drive is about 5 milliseconds to 8 milliseconds. It needs about that amount of time before it can start giving you back data for an operation. You wait about that long. Whereas with the solid state drive, it might be like 0.1 milliseconds. So this is an order of magnitude much better. There's random I/O performance. So another aspect of performance from latency, there's the number of IOPS per second. How many different operations can you do in 1 second? And then there's throughput as well that we'll look at as well. So there's 400 IOPS per second for a drive versus 6,000 IOPS for a solid state drive. So the number of operations, again, all of these numbers, when you start looking at them, they're orders of magnitude in difference, right? 6,000 operations per second for a solid state drive. The reliability, there's a half-life here or a failure rate of 0.5% versus 2 to 5%, and so on. I mean, this chart is in the printout. You can kind of see these things, and you can read more. There are some links down here where I got some of the information from, and see the differences between these different things. As I said before, from a computer organization point of view, they're starting to move from the typical SATA connection, which is sort of in the 6 gigabit per second range for transferring data, to the PCI Express bus, which has a lot more capacity for transferring and parallel data, doing a lot more operations per second. The PCI Express bus used to be used as well before for SCSI type buses for connecting drives, where you could daisy chain a number of drives together onto the one bus and so on. That used to go through the PCI Express as well, but then SATA came along and it's been with us for a while, the SATA connector, the way of transferring data, but now that's really changing over to the PCI Express with the MVM Express type controller, which tends to, it's eliminating a certain amount of controller overhead when we move on to that. So I don't really want to go right down into the computer organization and all the aspects of these controllers and the connectors and the pin layouts and that sort of stuff. I don't think that's really as relevant to you. It's just to understand that these things are changing quite a lot. It introduces a bit more of a hierarchy because, for example, I have now, and you probably have in laptops and other computers, will have servers and so on, will have some SATA drives and maybe some things connected here as well. Kind of creates another level of hierarchy between moving data up to something that's faster again than from a larger storage system, and it's still all in the one machine. So it's kind of interesting to see how the memory hierarchy is really changing. Here's quite a good chart actually that I found. Again, you can see it here at the link if you want to look at some more details. There's a nice report here outlining quite a few things, but it gives for a range of different, so these are hard disk drives up here, and then these are mSATA. mSATA is a little bit older type SATA, and then SATA solid state drives, and going down through this list to PCIe, and some of these numbers are just phenomenal in terms of the throughput, the changes in throughput that we're getting. Down here, 2,000 megabytes per second, 2 gigabytes per second of data rate, right, from the drive to the main memory to transfer, compared to something like 100 megabytes per second on some of the best high-speed drives, and 15,000 RPM drives. So that's a very big jump in terms of performance. This is on random reads and this is on random writes. So there's some details in terms of does the workload, is it mostly reading, is it mostly writing, What kind of application is it? Because these, the read times and the write times can be quite a bit different. You start looking at RAID systems, the reading and writing could be like half the speed of one another and so on. So depending on what you're doing, then you kind of need to take that into account. And the response times, as we said before, for some of these, this is kind of maximum response time over a set of measurements, and an average response time. And the average response time going down to 0.05 milliseconds for an SAS RAID, which is a serially accessed SCSI SSD type configuration. Very low response times, actually. It's incredibly low, and even the average, the maximum response times outperform, or very close to it, looks like the average response times for these hard disk drives. So there's a bit more data there, but I'm not going to go over the entire chart. But I mean, it's quite revealing. The cost per gigabyte of drives has been dropping, mainly because, of course, there's so many people, big companies buying disk drives, and the market, the price has plummeted considerably from the 1980s, where you might spend like $1 million for a gigabyte, all the way down to just 10 cents for a gigabyte. There's a similar kind of chart here, and again, you can't really see the times here, but this is a shorter time span. But for SSD, the cost is going down, and a bit of a chart here about the reliability or the failure rate of drives, and the SSDs all tend to come down to be more reliable and so on. So now I have just some discussion of what affects these times in the technologies. This is really just low-level discussion of disk drives, hard disk drives, and some solid-state drives, just to kind of look under the hood and see, what is happening. And first off, the I/O is pretty much the main differentiator of your computer classes. It's not so much the CPUs. You'll often have more CPU power in just a simple desktop computer. It'll be a faster CPU, in some sense faster clock speeds and so on, than you'll have in a mainframe. But in the mainframe that's servicing a lot of people, but the mainframe is giving greater performance because it's the I/O that's really the bottleneck, mostly in pretty much everything. Loading the data in, writing the data back out, that's where the bottleneck really happens, and that's what will be the differentiator. So the mainframes and the bigger systems will typically have a lot more I/O. That's something that you get when you distribute as well. If you distribute the data across a large system, you're getting now parallelism in all of the reads, right? You can read all at once now from all of those computers all at the same time. You can write all at once to all of them. So you've got a lot of parallelism in the reading and the writing by doing that. Map-reduce paradigm, for example, we'll talk about later. Mapping out to a large number of computers. They can all read then, from files there and write back down all in parallel. It gives you a lot, of improvement. So that is the differentiator. From a kind of queuing theory perspective, two things that we look at is throughput and latency. Has anybody studied queuing theory? Maybe one or two people. So it's a fairly hard area, actually. A lot of statistics in it to understand. But what we understand is that you can't have high throughput and low latency. It's a trade-off. If you want high throughput, the way that you obtain high throughput is to make sure all of your computers are queued up with jobs waiting to be run, so that all of the machines, all of the processors, all of the disk drives, if you like, from a storage point of view, always have something to do. Therefore, that they're working 100% of the time, and that is maximizing the throughput. But if you do that, then when you submit a new job or a new task, it will end up going into a queue and waiting because it's already a very busy system. So while you maximize the throughput, you're increasing the latency of new jobs. They sit in a queue and they have to wait. And indeed, the system can become unstable. It could be that if the arrival time of work to the system is, even if it approaches the theoretical throughput of the system, you can end up with queue sizes going up and becoming very large, and it becomes what we call unstable. Indeed, then you might start getting jobs being refused because the buffer size is full, and it can't take any more work, or jobs get dropped, they're just lost, they're deleted, because that's another solution. When you have too much work to do, you just start dropping some of it. And that can happen even if you're working close to the maximum theoretical throughput, because it's never really possible to say that the machine will do, if it does 10 jobs per second, it's not really doing a job can take 10.1 seconds or 9.8 seconds. It's a random variable. Actually, you go to queuing theory, you see it as a random variable, and the randomness produces variations in the load, and the variations lead to queue sizes getting bigger and bigger, even though you haven't reached the maximum rate of the system. We're looking a lot at this now in stream processing, where we have a lot of buffers in a system and a lot of jobs coming in, and we have the workload and the stability is very important. If it becomes unstable, then the system starts pushing back, and then you can get into some very weird bad performance type situations where it's kind of waiting and then doing a lot of work and then waiting and doing so. The queuing theory, I'm not really going to go into a lot of queuing theory. I have a PhD student who's studying queuing theory for these big data type systems to see how we can look at stability in really large systems, but we won't really cover in this course. And latency is harder to improve. This is saying you can't bribe God. I don't know where the saying came from, but it's basically just saying that latency is a function of latency is distance. And it takes time for a signal to travel from one place to another, and even if it's optical fiber, it's still going to take time, and that time you can't really make any shorter. Whatever that distance is, you have to pay that cost in terms of latency. There's nothing really you can do there. It doesn't really matter how much more optical. You can have a really many more cables and a lot of parallelism, but you have to take the time to go from one place to another. And if it's a distributed system, again, the latency can really build up into 100 milliseconds of ping time, or more, 250 milliseconds if it's like on the internet and going to the other side of the world, for example. It could be larger than that if you're going through, maybe wireless stuff. And a lot of data centers these days, the large data centers are moving towards wireless inside the data center even, so there's no cables, they just put the machines and it's all wirelessly connected because it's so easy to do. You don't have to plug cables in and so on, you just put the machines with wireless adapters. So this kind of thing can introduce, though it might be easy to do, it can introduce latency and even reliability issues. If you're working with mainframes and big data processing, cloud computing, this kind of thing, usually you're worried more about throughput though, so you want to maximize the throughput. The latency is not too bad. If it's stream processing, like I do a lot of real-time processing, trying to get a result in real time. So what we do a lot of is reading tweets from Twitter, and then we process and we try to come up with something very quickly, what's happening. Then maybe you're worried about latency because you want that to be real time. But if you're processing large amounts of data, typically it's throughput. And if it's a personal machine, then maybe you're worried about latency. If you push the key, you type something, you want it to happen immediately. So there's a few things to think about. There's caching as well. So the caches we talked about in the memory hierarchy. So as data is read into the computer system, then it's caching data. And there's a certain amount, there's multiprocessors. You have to think about consistency, the reading and the writing of the data, and so on. And you can have consistency in data if you kind of force a serialization of all of the that's one way to get consistency, but it's not really a good way because it reduces the performance quite greatly. If you start, then you don't really get any parallelism anymore. So you need to think about how you're going to do that. And a lot of the ways people are doing that today is to make the data such that the data comes in forms of tuples, a key value type storage, and it's kind of it's immutable. Once it's written, you don't change the tuple, so you can be read in parallel. It'll never change, so you get rid of the problem of consistency of changes. Even you don't really delete data anymore. Nobody deletes data, it just keeps building up, just keep buying more hard drives, keep storing the data somehow. So because it doesn't change, you get rid of these issues with caches. But it does mean that the storage can increase quite a lot, and it's all faster, so-called NoSQL type approaches to storing data. And this is talking a lot about the CPU and the memory hierarchy, and what I was talking then is a larger distributed type system, but same sort of concepts. So what people try to do is to balance the ratios of these things. So if you've ever been doing a big computation that's processing a lot of data, reading from the disk, maybe it's doing video processing or something like that, and you've had a look at what is busy and what is not on say a resource monitor on the computer, you'll see maybe the CPU is like 10% busy and the disk drive is 100% busy. Right, which means you're bottlenecked now at the disk drive. The CPU is not doing much, it's just waiting for the disk drive to get the data into so it can do the processing, right? Or it might be the other way around. The CPU is 100% busy and the disk drive's maybe 10% busy, right? Which is the other way. Now that it's a computational problem that you have, right? The disk drives aren't doing much. So it would be nice though if this thing were balanced so that the two things, so you have, you don't have too much CPU and you don't have too much I/O. You haven't spent too much money. These things cost money, obviously. So you balance the computations out, configure a system that does do something that's cost effective and also efficient. So you can sort of balance it. There's some really old quotes here. Some of this material comes from an old course that I taught about 5 years ago, and so some numbers. But anyway, so typically it does depend a lot on the amount of of the cost of things as well. So what affects hard disk drives? Hard disk drives, as you probably know, but I'll just reiterate now anyway, are they spin. There's a disk that spins, and there's platters. They're called. There's heads like this that move like that over the platter, right? And the spinning time. The head is called seat time. So the time it takes to get to there's a disk has tracks, and the time it takes for this head to get to the track is the seat time. Then the head has to sort of wait for the disk to spin so that it can read the right piece of data, right? So there's a sort of rotational delay there as well, a latency, and then there's transfer time just as the disk is spinning, then it has to, the head has to read off that disk drive into a buffer somewhere and transfer the data, and some other things, setup and completion overheads just in the controller itself of the disk drive. These are the sort of things that affect the time. So obviously the faster the disk is spinning, the less the rotational latency might be, and so on. And so you want faster drives, faster spinning drives to get lower times. So, and it can, as I said before, I mean these times can depend a lot on the OS or the database that's being used. So, if the operating system can know about the data, what is going to be accessed, it can put the data onto the disk in a way and such that it's contiguous. When it's spinning, it's all the right data, and the head just moves one track and then the next data. And so we often talk about, you might think in OS sometimes we say defragmenting the disk. So all the files are laid out in a way such that the disk access is, we reduce the seat times and the rotational latencies. But you can do that with databases. You can do that in the big storage systems. Obviously, these things are happening under the hood to try to make sure that we're getting the best effect. Now that's for disk drives. For solid state drives, the situation is very different. We don't have these mechanical parts. And I just have this diagram that I found seems to be okay. So with the main things with a solid state drive is that it's essentially like a little computer. It has banks of memory. These are channels. These are the banks, so there's M banks and there's N channels in this solid state drive. And these are really just like RAM in some sense that has controllers to read and write to these NAND gates. And then and a DRAM controller as a buffer, essentially a DRAM chip, and then a host controller. And there's a microprocessor here in the solid state drive. So what are the things that kind of contribute? So you have a microprocessor, you have channels, you have banks. The delays include very much the firmware processing. So the microprocessor has some kind of program on it that is doing some kind of complicated queuing of jobs. So as IOPS come into the thing, which job should I do? Which read? Should I do a write first? Maybe we can reorder them and do them in different order to try to improve the performance, because you want to try to get parallelism out of all of this. Where the data, how the data is spread over this, we like to try to get some parallelism. So there's just NAND waiting time, just the time it takes to invert a bit electrically on one of these NAND gates here, and then there's DMA transfer, just transferring between the NAND and the DRAM chip that's on the controller. So this firmware overhead is not negligible, and a lot of people are doing work and trying to make the firmware better. The architecture itself can use pipelining and super pipelining to try to get more parallelism inside that solid state device, right? Solid state drive, we could call. So there's a lot of interesting stuff there, but it's all kind of electrical engineering, right? But nevertheless, these things are, how does this fail? Obviously, as Udaya said, there's correcting codes at all levels, and at the memory there will still be correcting codes. You don't see them, but they're there. So if maybe a little bit fails, this whole device can still work, it will recover. But if too much fails, then maybe the whole device goes down or a certain channel goes down, and this may affect the way that you work with the device at a higher level, what kind of system that you work. We talk about dividing things up into sectors and blocks, and very, very typically this all came about from the disk drive days. You have a disk and it has sectors, and the way that it was all divided up. And then you can read, you tend to read more than one sector at a time. You read a block of data because if you read consecutive sectors, then it can be a lot faster than reading randomly sectors from around the place. I used to work with tape drives, storing things on tape, and that was a lot worse, right? Then you had this huge latency when you needed to go from one place to another on tape drive, because it's a sequential kind of thing. So that's kind of how you would operate format the disk. Now, we sort of talked a bit before, but so the disk performance is broken into these three parts. There's a transfer rate, and you might try to maximize that if you have large data sets and like image processing. You would want to increase the transfer rate, because you're really just reading huge amounts of data and maybe just running some fairly basic calculation over the data, but reading a lot of data. And it's usually very sequential as well. It's not random access anymore. You're not just reading different parts of the data from different parts of the system, but you have a lot of sequential access. So that's just limited by the rotation rate of the disk drive if it's a disk drive. In the solid state drive, that'd be just limited by the times that we said. Probably the DRAM transfer rate would be the limiting factor there on the solid state drive. So there's that. Then there's as well, it depends, maybe you have an application like file serving or transaction processing where you've got a lot of little bits of data and they're all spread out everywhere, and you're just reading randomly. It's random access essentially, and writing randomly. And then you would want to, the important thing is the number of IOPS, the number of IO operations per second that this system can supply you with. That'd be more what you'd be worried about. Now you can improve that by adding more arms to a disk. So if you have a disk with maybe 2 arms, you can have 4 arms or something like this, or 2 arms on either side. You can do things mechanically if it's a solid state drive. Perhaps in the IOPS per second that was the hard disk drive. In the solid state drive, you would do maybe you would improve the firmware, or you would do something to increase the parallelism so that you can increase the number of IOPS per second. So you can always use a lot of smaller disks instead of one larger one as well. And in part, that's what when we go to some of the basic RAID is that there's no real redundancy. In some sense, it's not really RAID, but you have a lot of disks all operating in parallel in order to get you more IOPS or more throughput or something like that. So in that sense, you talk about striping, and Udaya mentioned that as well. It's a straightforward disk setup. Some disks, if you just don't do this, then you get very unbalanced access. Some disks don't get any access, other disks get all the access, and maybe your typical laptop, you've just got a bunch of disks, right? Just a bunch. It's actually just called that, just a bunch of disks, and some of them you're not really getting good performance. You could do striping or interleaving over the two disks, and it puts odd number blocks on one and even on the other, so there's no redundancy. It's just there for performance. I have that at home. I have 3 solid state drives that are all rated with RAID 0. And so I got this, and it really does increase the performance. I've got like 3 times the speed. It's quite good way to do that with. So it evens out the load, it doubles the transfer rate. But sometimes, and you'll see, and we'll talk about before, maybe you have to have, for a single write, you might have to have both the drives working together, or the heads of the drives, or whatnot. So there's a choice. How do you do that? Track cylinders or groups. That choice is obviously going to be a little bit different, the way that it might work on solid state drives. This is in terms of hard disk drives, but it is a choice that needs to be made, and to somehow optimize the performance of the storage system. Disks have caches as well, and I didn't point it out, but on the very first slide, or the first couple of slides where we looked at some numbers, there was part of it that said write cache disabled, and it was disabled for pretty much all of the run times. But then there was one of them was write cache enabled, and on the maybe I could go back to it, but the write cache enabled, with the performance was much greater, because the disk drive itself was caching data and so on internally. It wasn't writing immediately. It would maybe write after some, when it got to it. But the problem with caches is, if you have a power failure, then the data that the operating system thinks has been written to the disk may not have actually been written to the disk. It might have failed. You need a bit better disk. It needs to have enough battery backup. Make sure that the cache system can write properly and finish all the operations, so that you don't end up with a corruption somehow with the disk drive. So there's caching that happens at that level as well. Another aspect that you need to think a lot about, and I did talk a little bit about it, is I/O buses. These things obviously can become a bottleneck to the performance of the system, transferring between the storage thing to the main memory of the machine. And if you've ever if you work in the area, if you spec'd out machines and looked at, there's a wide variety of things there to consider, and more so today than ever with M.2 type interfaces, and there's just a large amount to consider to get it right, so that you don't have a really big bus that's actually not being used very much because the drives aren't pushing that much data, or huge drives with huge performance but a really bad bus that doesn't really allow the drives to work at their maximum rate. So you need to consider all of the parts, so that you don't have a bottleneck somehow that comes up along the way.